So let me get the samples so we can try to get the process here. So let me just get one like they have on the exercise and cumulative review. So I want to just do the outlier part. So I'm going to have to take that sample to rearrange it and to see if there are any outliers or not. So let me get this board for this. So I need to do two things and copy this sample and to also arrange its elements from the smallest to the largest. So let's see, the smallest seem to be a negative 241. 241 here. And we get a negative 151 and then 125. So this is a procedure that I guess I'm not going to expect you to do on the tests. I will give you samples that will already be pre-arranged for you. So minus 85, minus 65. Any more negatives? Then looks like that's it. Okay, so then I have a pair of 20s. So now we look at the positive sample elements, 20s. Then there is a 30, also element 40. Oh, there's 27 here also. Almost missed it. That's no good. So 27, then 30, and then 41. Okay. 27, 30. This is an annoying part in a way, annoying part, right? This part sometimes takes a while, but little by little we're getting closer to the end, and that's good news. So 80, then 105. So we're almost done with this. And then it's 186. 140 comes first, then 186, and finally the largest entry here, which is 325. I think that's all the sample has. Cool. So how many elements are here? 4, 6, 8, 10, 12, 14, 15 sample elements. Okay. So I will recall how we produce the box plot. So the picture of the box with first and the third quartiles that produce it. So I need to find those first and the third quartiles. So let's go for those. First and the Q3. So for the Q1, I take 25% of the sample elements. That's another name of it. 25th percentile. Or for the third quarter, that will be 75%. So we'll take 0.25 and multiply by the sample size n, which is 15. So when I do this, I'll get 3.75, 3 3/4. And when I do the same with multiplying 0.75 and times again sample size of 15, then this is 11.25. So these two numbers are both decimals, so we move to the next position. No, we don't round them, we just select the elements on the next positions. So these be elements number 4 and elements number 12. So the fourth position is here. Then 6, 8, the other thing. 6, 8, 10s, 12s, 14s. So 12th position is here. 12s. Okay, 12th position. So we found these two special numbers. One of them is negative 85, and the other is a positive 105. So those are percentiles that we used to look for. We also used to find median, the middle element of the sample, or 50%, half of sample elements. So this is a 7.5. It's another decimal. So same as in the previous steps, I move to position number 8, and then we get someplace here where we have our median 24 or 27. So of course we can check and see that this is making sense in terms of splitting your sample here into 4 groups that have 3 elements in each. So you can see that if I have the third quartile here with -5 element, actually the first quartile is -85, and the third quartile was element 105, and my median is in the middle here, then looks like these quartiles will split into quarters, the elements of sample that remain. So there will be 3 elements in each of 4 groups. So that supports the fact that we are on the right track, and that feels better a little bit. So now I need those special fences so we can see where those outliers are supposed to be. So these fences have special names: inner, right, and the outer fence. And same on the other side. There's inner fence and also outer fence. So I need to now look for the gap in between of those quartiles. So since one sits at -85 and the other sits at 105, then I need to subtract from 105, subtract number -85. So there actually be 2 minuses. And this is how we find this range in between quartiles, interquartile range. And we're actually going to have to add, not subtract, right? Because 2 minuses is a plus, or you can just put this in a calculator to make sure you do it right. So this interquartile range is a key to produce fences, but you have to times it by 1.5, and that was the rule that we encountered in that section. So I just have to keep that rule in mind, I guess, and multiply by 1.5, that 190 that I just produced. So 185, right? Yes, this number is the most important for us from now on, because we going to use it to get the fences. So we'll start at the right side of the box and go 185 farther to the right once and once again, 2 times. And then we start on the left side of the box, and then we again use the same 185, so we'll be subtracting it. So that's how we do construction. So the key number 185 is going to be heavily utilized here. So I will go from the right side of the box where 105 is, and I'm going to add it with 185. So just do some arithmetic here, and we get a 290, looks like. So this is where I put my fence. So do this once again, 290 and 185. So we are moving to the right. So we're adding them. So it looks like this will be 475. And that's a position for the second special fence. And then start on the other side, on the left side of the box where negative 85 is, right? And then we move again by 185, but since it's in the other direction that we're gonna subtract. So negative and negative, I actually put together and keep the minus, so it'll be something like minus 270. And then once again, I subtract that 185 and get the last fence, even though probably I don't need it for this particular sample, but just to finish up with this process. So we see that it really follows this procedure of using that 1.5 of interquartile range, or number 185 that happened to be the one that I keep on adding. Well, so now it's time to go back to the sample and see what is going on in reality. And with this particular sample that starts on the left side at minus 241, I don't have any outliers on the left side because negative 241 is not farther beyond the fence, because minus 270 is farther to the left than minus 241. So I can show it like that. So I put this little thing, sample start. And the other elements will be when closer to the center of sample. So I'll just go to the other direction, to greater side, where I saw 325. And then I need to decide if this is going to give me anything or not really. And one can say, Alex, you did miscalculation here. I think it's great that I did, because I didn't wake up, looks like, because I put 185, but that should be 285. I just looked at the number and I said to myself, Alex, how come 190 and 185 is smaller? So it should be 285. It should be 285. So it's a good idea that I noticed. Did you notice it? See, I think it's great that I made that miscalculation, because now you know that we need to use a calculator, right? It's a good idea to use that little tool, calculator. So this is actually 390, and this is actually going to be 575, right? So it's not hard to fix, but it could give you the wrong results. So 390 is here. And then when I move to the other direction, it will be 285 here, right? And 285 here. So this is going to be like 370, right? 370. It doesn't do anything with the previous, but it still should be fixed, right? And then if I add this, I'll get 5. 55. Looks like this way. So I guess these outer fences are irrelevant anyways, but we want to be careful when we calculate. So it's great that you also notice this. So now I feel better. So now I can see that 325 is smaller than 390. So that 325 is fine because we are within the range. What does that mean? Well, here's our range. Here's the fence, and here's the other inner fence. So these two inner fences show me where the sample elements should be, and my sample elements are where they should be. They are within fences. So my answer is there are no outliers at all. So the whole sample is good. So if you want to use its elements to find mean, standard deviations, maybe something else, then you can use all of its elements. Don't throw any away because your sample is within the allowed range. So that's what means that sample elements are good. So there are no outliers. And that's actually also important information. So don't get disappointed because not all samples have outliers. I think last time we found one with outliers, but some samples are just fine. So problem here was pretty lengthy, right? Lots of little steps. So the advice is over coming weekend, try to do this exercise again on your own. I will eventually do one more exercise of this type, of course, because this process is something we need to get used to. It is important process for applications. And I would like to make you happy. I would like to show you chapter 3, where problems will be much, much shorter, because this is just too long, one can say. And I would totally agree, it's just too many steps, the quartiles, outliers, the fences, all this. So what I'm going to do is I'm going to end it for now. So I'm going to just share back the textbook and scroll down to the chapter 3, which is starting right here on the next page. And notice that section 3.1 does not have any exercises in it. Well, remember, this is how this book is designed. First sections of every chapter, there's just an overview of what you're gonna see. So I don't wanna look at it at this stage because you will see all that anyways. So this chapter is called probability. And it's definitely important to know what is that they're talking about. And it turns out that probability is a fraction. So I will create a convenient experiment for you so you can get a better feeling what this is all talking about. So I'm sure you saw this little cube, which is called a die. It has 6 sides and it has different numbers of dots on each side. So there are sides with 1 dots, 2 dots, and etc. all the way up to 6 of these little dots. So people usually play games with this die, they roll it and see what they got, right? So I'm sure you're already familiar with this. So that's why I want to select this cube and show all the possibilities that one can get if you roll it, this cube, 1 time. and we assume that there are just 6 choices here. So there is no way you can just roll it and it falls in the ocean and you don't know what's on it, or other thing that may happen, you roll it and it sticks somewhere and it sits on the edge, so you don't know what is the top face of this cube. So we assume we prepare some nice place like a table, so we can roll the cube carefully on that table so nothing happens. So we get from 1 through 6 outcomes of experiment of rolling this little cube. So there are 6 choices. So now I'm gonna calculate some probabilities related to it. And the probability that I can count, I can actually calculate various probabilities. Some people say, Alex, I'm so lucky, I always get 6. Whenever I roll this little cube, I always get 6. So I want to find a chance of this to happen. And out of total number of possibilities that I just listed above, it turns out there is only one that satisfies to the statement to get 6. So people say the chance of it is 1 out of 6. And that's how they designed this formula. So we produced fraction with a denominator that has a total number of choices, or that's so-called sample space. So entire sample of all of the possibilities. So we put that total in denominator, and in numerator, we put the number of possibilities that we're interested in. So it'll be only 1 because there is only 1 6 that I can see. You can find also various other probabilities. Let's say, what's the probability that someone rolls this cube and gets only 1 on it? Well, this is going to be the first one, right? And looks like out of 6 possible choices, again, there is only 1 that satisfies to this experiment. So it's also 1 out of 6. So there are various questions possible. For example, someone can say, well, I need 7. I want to roll and get 7. What's the chances of that? So out of the 6 possibilities, how many 7s do I have? I don't have any 7s, so it's a 0. It is a 0 chance. And this actually tells me that the lowest possible probability is 0. Because you always have a fraction with denominator 6 in this case. But for a numerator, the lowest I can get is nothing, 0, if there is no chance for that to happen. So I cannot go lower than 0. I cannot get negative probability. And that's important to realize. How about if someone just to win already has plenty of those dots, whatever, they rolled it a few times, and now they say, I need at least 1, and I already won this game. So what will be a chance that if I roll this little cube, then out of my 6 possibilities, I will get 1 or bigger. So 1 is here, or bigger, which is 2, 3, 4, looks like all 6 satisfy to such a statement, right? And this is equal to 1. So it turns out the largest probability that I can possibly get will be taking all of them, all 6 out of total 6. And since this is the largest, I will say my probability cannot possibly exceed number 1. So the answers, whenever you have question about probabilities, are always in between of zeros and ones. No negatives, no 200%. Some people say 200% sure. 100% is enough. That's it. 100% means that you get it. And that's it. You don't need to increase it by more percents. So 100 is maximum. I know that in other classes, in some economics, your profit may be doubled or even tripled. So you will get 300% profit. It is possible, of course. Or you get negative profit when you get lost, but not in this class. In this class, when they say word probability, the key rule here is that probability must be in between 0 and 1. And if your answer is not in between, well, then there is something miscalculated and you've done something wrong. So that just should tell you that you need to double check your work and fix it. So probabilities are always between 0 and 1. That's the first rule for probabilities. So I'd like to start doing some problems in this section just to start today. And of course, we'll continue with this farther and farther. We'll be dealing with this chapter for a while. So exercise number 3 here asks interesting question. Which one cannot be probabilities? Cannot. So what answer you cannot get for a probability? And I would say negative, right? No negatives. Yes, yes, very good. So -1 is not allowed. So no negative probabilities. 0 and 1 are fine, but no negatives. What about 5/3? 5/3. That's something like 1.6. Or square root 2. That's 1.4. Looks like these two numbers are also no good, just like number 2, right? Because we should not be bigger than 1. So 5/3, a root of 2 are out. We cannot have them for the answers either. So only 4 values that left possibly could be probabilities, but definitely not those out of range. How about problem number 5? I think that's an interesting exercise that gives you exciting story about the list of 8 outcomes that come out when couple has 3 children. So let me see how those possible outcomes appear if there are 2 genders for a child, either girl or boy. So for the second child, if first child is a girl, well, second child could also be either girl or boy. So the previous gender doesn't really matter. And same if my first child happened to be boy, then, well, for the second child, still it's either girl or boy. And analogously, I can continue with genders for the third child. So either girl or boy, no matter what happened before, it's either girl or boy for the genders. So I'll just continue the so-called tree diagram. This is very important and useful diagram when you want to list all of the possibilities if your sample is pretty small. And say, okay, Alex, where are those 8 possibilities? It's just a bunch of numbers. Well, if you now start here at the beginning and follow along the branches of this tree, then you end up with a first chance as 3 girls, the genders for 3 children. Or if you now go along the same branch, but then sink down a little bit. So you will get first 3 girls, but first 2 girls and the third child, a boy, and etc. So you can get a girl first, then boy and a girl, and then girl and 2 boys. And these are the possibilities with the first child being a girl, because now we're going to go with the lower part of a tree with the first child being a boy, and basically go with the same exact possibilities for the other 2 children. So first is boy, I can also have girl and then a boy. And then if first is boy, then second can also be a boy, but the third could be either girl or a boy. So those are 8 possibilities that they're talking about, or 8 outcomes of our experiment. So when I calculate answers for parts A and so forth, I will have 8 in my denominator. So if they say in a part A, find the probability that there's exactly 1 girl. 1 girl exactly. They don't tell you if that's a first child or second child or third child. All I know that out of 8 possible, I can have girl to be either here, first child, or there, 1 in the middle, the second child, or girl could be the third child. So it's 3 out of 8. Very good. So you already see this, and that's super. So let us do another part, B. Part B says, how about if there are 2 girls? Please notice that having 2 girls is equivalent to say, what's the chances to have 1 boy? Because according to genders, if there are 2 girls, then 1 last child should be boy, or the middle should be boy, or the first should be boy. So it's similar to the previous in a kind of dual way, right? So we can also see there are only 3 out of total of 8 that satisfy to this experiment. So that's great. Great that you see it. I hope you start to like this exercises because they are shorter. Because all you do is you just produce a fraction, something in denominator and something in numerator, and you're done. And that's definitely way less time consuming compared to previous sections. So the last part of this says, what about if all children are girls? So out of 8 possibilities, how many have all girls? I can see only 1. 1 out of 8. 1/8 is an answer, and that's great. So it looks like you feel comfortable with this. So maybe I will ask you to also find the probability that there are no girls. So for a little quiz for today, please don't hurry. Find what is the probability that there are no girls in the family. And as usual, just put the answer in the chat. So same exact story, same exact setting, and it's all in front of you here. But the answer will be, of course, fraction, right? And once you produce this fraction, well, you're done with the quiz. Someone already did it. That's great. So after that, you can relax a little bit. You deserve it. So no girls, or yes, equivalent. They're all boys. Exactly. So you